Hello and welcome to Earth Science, Lecture 34, The Sun. The Sun is the largest member of the solar system. It has almost 1,000 times more mass than all the planets, moons, asteroids, comets, and meteoroids put together. It is a remarkably typical star, however, with a mass, size, surface temperature, and chemical composition that are roughly midway between the extremes exhibited by the myriad of other stars in the heavens. With both chemical processes and gravitational contraction ruled out as a possible explanation for why the sun shines, scientists were at a loss in the past. There was no known way that an object the size of the sun could generate so much energy for billions of years. A completely new type of explanation was needed, and it came with Einstein's publication of his special theory of relativity in 1905. According to Einstein's special theory of relativity, a quantity m of mass, measured in kilograms, can in principle be converted directly into an amount of energy, E, recorded in joules. According to a now famous equation, E equals mc squared, where c is the speed of light. A small amount of matter can release an awesome amount of energy. For example, if the mass in just 1 penny, which is about 2.5 grams, were completely converted into energy somehow, it would release about 5 times the energy of the nuclear bomb that detonated over Hiroshima. Calculations immediately showed that the sun's mass contained more than enough energy to account for billions of years of sunshine, if the sun could convert the energy of mass into thermal energy. Fusion occurs within the sun because the 15 million degree Kelvin plasma in the solar core is like a soup of hot gas, with bare, positively charged atomic nuclei and negatively charged electrons whizzing about at extremely high speeds. At any one time, some of these nuclei are on high-speed collision courses with one another. In most cases, electromagnetic forces deflect the nuclei, preventing their actual collisions, because positive charges repel one another. You've probably heard this, right? Like charges attract opposite charges attract and like charges repel. So if nuclei collide with sufficient enough energy, however, they can stick together to form heavier nuclei. Sticking positively charged nuclei together is not easy. The strong force, which binds protons and neutrons together in atomic nuclei, is the only force in nature that can overcome the electromagnetism between two positively charged nuclei. In contrast to gravitational and electromagnetic forces, which drop off gradually as distance between particles increases, the strong force is more like glue or Velcro. It overpowers the electromagnetic force over very small distances, but is insignificant when the distance between the particles exceeds their typical sizes of the atomic nuclei. So the key to nuclear fusion, therefore, is to push the positively charged nuclei close enough together for the strong force to outmuscle electromagnetic repulsion. In other words, you basically need that Velcro to stick. The high pressures and temperatures in the core of the sun are just right for fusion of hydrogen nuclei into helium nuclei. The high temperature is important because the nuclei must collide at very high speeds if they are to come close enough together to fuse. The higher the temperature, the harder the collisions, making fusion reactions more likely. The high pressure of the overlying layers is also necessary, because without it, the hot plasma of the solar core would simply explode out into space, shutting off the nuclear reactions. So let's investigate this fusion process in the sun with a little bit more detail. Hydrogen nuclei are simply individual protons, while the most common form of helium consists of 2 protons and 2 neutrons. The overall hydrogen fusion reaction therefore transforms 4 individual protons into a helium nucleus containing 2 protons and 2 neutrons, like you can see in the image at the top. This overall reaction actually proceeds through several steps involving just 2 nuclei at a time. The sequence of steps that occurs in the sun is known as the proton-proton chain, since it evolves from the collision between protons, or hydrogen nuclei. So note there are a series of steps in this proton-proton chain, but it is a little bit beyond the scope of the class, at least in the time that we have. And so if you'd like to look into it more, just look it up and take a look at what those actual steps involve. But the overall reaction, again, is that 4 hydrogen nuclei, or protons, somehow fuse together to give us a helium nucleus with a little bit of energy left over. So that's where the interesting part comes in. Where's this energy coming from? Well, remember, E equals mc squared. Fusion of hydrogen into helium generates energy because a helium nucleus has a mass that is slightly less, by about 0.7%, than the combined mass of the 4 hydrogen nuclei. That is, when 4 hydrogen nuclei fuse into a helium nucleus, a little bit of mass disappears. The disappearing mass becomes energy in accordance with Einstein's formula E equals mc squared. About 98% of the energy emerges as kinetic energy of the resulting helium nuclei and radiative energy of gamma rays. As we will see, the energy slowly percolates to the solar surface, eventually emerging as the sunlight that bathes the Earth. Neutrinos, another particle created in these collisions, carries off the other 2% of the energy. Overall, fusion in the Sun converts about 600 million tons of hydrogen into 596 million tons of helium every single second, which means that 4 million tons of matter is turned into energy every second. Although this sounds like a lot, it is a minuscule fraction of the Sun's total mass and does not overall affect the mass of the Sun in any measurable way. Luckily, the Sun's core contains enough hydrogen to have been giving off energy at the present rate for as long as the solar system has existed, and that is about 4.56 billion years. And it will continue to do so for more than 5 or 6 billion more years into the future. The solar thermostat balances the Sun's fusion rate so that the amount of nuclear energy generated in the core equals the amount of energy radiated from the surface. However, the journey of solar energy from the core to the photosphere takes hundreds of thousands of years. Most of the energy released by fusion starts its journey out of the solar core in the form of photons, that is, little packets of light. Although photons travel at the speed of light, the path that they take through the Sun's interior zigzags so much it takes them a very long time to make any outward progress. Deep in the solar interior, the plasma is so dense that a photon can travel only a fraction of a millimeter in any one direction before it interacts with an electron. Each time a photon collides with an electron, the photon gets deflected into a new random direction. The photon therefore bounces around the dense interior in a haphazard way, sometimes known as a random walk, and only very gradually works its way outward from the Sun's center. The technical term for this slow outward migration of photons is called radiative diffusion. To diffuse means to spread out, and radiative refers to the photons of light, or radiation. The Sun is not undergoing any dramatic changes. It is not suddenly expanding, it is not suddenly contracting. This is because the Sun has achieved a balance called hydrostatic equilibrium, also sometimes referred to as gravitational equilibrium, between the outward push of internal gas pressure and the inward pull of gravity. The outward push against gravity comes from the internal gas pressure as energy radiates outward from nuclear reactions in the core. The Sun's internal pressure precisely balances gravity at every single point within it, thereby keeping the Sun a stable size. A human pyramid provides a simple example of this type of gravitational equilibrium. The bottom people support the weight of everybody above them, so their arms must push downward with enough pressure to support all this weight. At each higher level, the overlying weight is less, so it is a little bit easier for each additional person to hold up the rest of the stack. Gravitational equilibrium works much the same way in the Sun, except the outward push against gravity comes from, again, that internal gas pressure rather than the people's arms. The Sun's internal pressure precisely balances gravity at every point within, thereby keeping the Sun stable in size. From the center of the sun out to about 0.71 solar radii, in other words 71% of the radius of the sun, energy is transported by radiative diffusion. Hence, this region is called the radiative zone. Beyond about 0.71 solar radii, radiative diffusion is no longer an effective way to transport energy due to the low density of the gases in the sun. Instead, convection dominates the energy flow in this outer region, which is why it is called the convective zone. The differing temperatures and densities of the plasma at different depths give the sun a layered structure. All of the sun's visible light emanates from a single thin layer of gas called the photosphere, where the temperatures are roughly 5,800 degrees Kelvin. Just as you can see only a certain distance through the Earth's atmosphere before objects vanish in a haze, we can only see about 400 kilometers down into the photosphere of the sun. This distance is so small compared to the sun's radius of 696,000 kilometers that the photosphere appears to be a definite surface, like you can see in the image on the top. The photosphere is made primarily of hydrogen and helium, and has a density roughly 0.01% the density of Earth's atmosphere at sea level. Despite being such a thin gas, the photosphere is surprisingly opaque to visible light. This means that visible light is scattered numerous times as it passes through this photosphere. Because it is so opaque, the photosphere's spectrum of light is close to that of an ideal blackbody, meaning that it absorbs all light coming in. Under good observing conditions, astronomers can often see a blotchy pattern in the photosphere called granulation. Each light-colored granule measures about 600 miles across, equal in size to about the area of Texas and Oklahoma combined, and it's surrounded by a darkish boundary. The difference in brightness between the center and the edge of a granule corresponds to a temperature drop of about 300 degrees Kelvin. Granulation is caused by convection in the gas in the photosphere. Granules form, disappear, and reform in cycles lasting only a few minutes. At any one time, about 4 million granules cover the solar surface. An ordinary visible light image gives the impression that the sun ends at the top of the photosphere, like we see at the image here at the top. But during a total solar eclipse, the moon blocks the photosphere from our view, revealing a glowing pinkish layer of gas above the photosphere. This layer is known as the chromosphere, the second of the 3 major levels of the sun's atmosphere. The chromosphere is only about 1/10,000th as dense as the photosphere. Analysis of the chromospheric spectrum shows that temperature increases with increasing height in the chromosphere. In other words, the further away you get from the sun in this layer, the hotter it gets. This trend is just the opposite of the situation in the photosphere, where temperatures decrease with height. The temperature is about 4,400 degrees Kelvin at the top of the photosphere. 2,000 kilometers higher, at the top of the chromosphere, it's actually 25,000 degrees Kelvin. The corona, or outermost region of the sun's atmosphere, begins at the top of this chromosphere. It extends outward to a distance of several million kilometers. Despite its tremendous extent, the corona is only about 1/1,000,000th as bright as the photosphere, no brighter than our full moon. Hence, this corona can be viewed only when the light of the photosphere is blocked out, by use of a specifically designated telescope, or, as we see in the image at the top, during a solar eclipse. Temperatures in this corona, or outermost atmosphere of the sun, reach 2 million kelvins, or even higher, far greater than the temperatures in the chromosphere. Earth's gravity keeps our atmosphere from escaping into space. In the same way, the sun's powerful gravitational attraction keeps most of the gases of the photosphere, chromosphere, and corona from escaping. But the corona's high temperature means that its atoms and ions are moving at very high speeds, around 1,000,000 kilometers per hour. As a result, some of the corona gases can escape, and they do. This outflow of gas is what's called the solar wind. Every single second, the sun is ejecting about 1,000,000 tons of material in this solar wind. But the sun is so massive that even over its entire lifetime, it will only eject a few tenths of a percent of its total mass. The aurora, or northern lights, seen in the northern or southern latitudes on Earth are produced when electrons and ions from this solar wind enter our upper atmosphere. Energy liberated by nuclear fusion in the sun's core eventually reaches the solar surface, where it helps create a wide variety of phenomena that we can observe from Earth. Sunspots are only the most obvious of these phenomena. Because sunspots and other features of the sun's surface change with time, they constitute what we call solar weather, or solar activity. The quote-unquote storms associated with solar weather are not just of academic interest. Sometimes they are so violent that they affect our day-to-day life on Earth. Most of the sun's surface churns constantly with rising and falling gas. However, larger features sometimes appear, including sunspots, the huge explosions known as solar flares, and gigantic loops of hot gas that extend high into the sun's corona. All of these features are created by magnetic fields, which form and change easily in the convecting plasma in the outer layers of the sun. Sunspots are irregularly shaped dark regions in the photosphere. Sometimes sunspots appear in isolation, but they frequently are found together in sunspot groups. Although sunspots vary greatly in size, typical ones measure a few tens of thousands of kilometers across, comparable to the diameter of Earth, as you see in Part C of this image. Sunspots are not permanent features of the photosphere, but last between a few hours and a few months. Sunspots are the most striking features of this solar surface. If you could look directly at a sunspot without damaging your eyes, you would find it to be blindingly bright. Sunspots appear dark in photographs, however, only because they are less bright than the surrounding photosphere. So, the cooler the surface is, the darker it is, as we've talked about quite a while ago in our lecture discussing some of our information about light. So, in this case, it looks black because it's so much cooler than the surroundings. So, they're cooler at a temperature of about 4,300 degrees Kelvin, compared to the 5,800 degrees Kelvin in the region around. And so, the umbra of this, the darkest part, only emits about 30% as much light as an equally large patch of undisturbed photosphere, which is why they appear so dark. But if you were to somehow block out the light coming from everything around a sunspot, it would still appear bright. Solar magnetic field lines act somewhat like elastic bands, twisted into contortions and knots by turbulent motions in the solar atmosphere. Sunspots occur where tightly wound magnetic fields poke nearly straight out of the solar interior, as you can see here. These tight magnetic field lines suppress convection within the sunspot and prevent surrounding plasma from entering the sunspot. With hot plasma unable to enter the region, the sunspot plasma becomes cooler than that of the rest of the photosphere, and hence why they appear dark. Solar weather is just as unpredictable as weather on Earth. Individual sunspots can appear or disappear at almost any time, and we have no way to know that a solar storm is coming until we observe it through our telescopes. However, long-term observations have revealed overall patterns in solar activity that make sunspots and solar storms more common at some times than others. The most notable pattern in solar activity is the sunspot cycle. A cycle in which the average number of sunspots on the sun gradually rises and falls. At the time of sunspot maximum, when the sunspots are most numerous, we may see dozens of sunspots on the sun at any given time. In contrast, we may see few if any sunspots at the time of sunspot minimum. The frequency of prominences, solar flares, and coronal mass ejections, which we'll discuss in just a moment, also follows this cycle, with these events being most common at solar maximum and least common at solar minimum. The length of time between maximum averages 11 years, but we have observed it to be as short as 7 and as long as 15 years. Sunspots tend to occur in pairs, connected by a loop of magnetic field lines that can arc high above the sun's surface. Gas in the sun's chromosphere and corona become trapped in these loops, making giant solar prominences. Some prominences rise to heights of more than 100,000 kilometers above the sun's surface. Individual prominences can last for days or even weeks, disappearing only when the magnetic fields finally weaken and release these trapped gases. The magnetic fields, winding through sunspots and prominences, sometimes undergo dramatic and sudden change, producing short-lived but intense storms on the sun. The most dramatic of these storms are called solar flares, which send bursts of X-rays and fast-moving charged particles shooting off into space. Solar flares generally occur in the vicinity of sunspots, which is why we think that they are created by changes in magnetic fields. The leading model for solar flare production suggests that they occur when the magnetic field lines become so twisted and knotted that they can no longer bear the tension. They are thought to suddenly snap and reorganize them into a less twisted configuration in a process known as magnetic reconnection. The tremendous amount of energy stored in the magnetic field is then released into the solar atmosphere. A single arc contains as much energy as a hydroelectric power plant would generate in 1 million years. The amount of energy released in this way is thought to help maintain the temperatures of the chromosphere and corona to be so high. Flares and other solar storms sometimes eject large numbers of highly energetic charged particles from the sun's corona. These particles travel outward from the sun in huge bubbles known as coronal mass ejections. The bubbles have strong magnetic fields and can reach Earth in a couple of days if they happen to be aimed in our direction. Once a coronal mass ejection reaches Earth, it can create a geomagnetic storm in Earth's magnetosphere, in other words, within our magnetic field. On the positive side, these storms can lead to unusually strong auroras and can be visible throughout much of the United States. But, of course, on the negative side, they can hamper radio communications, disrupt electric power delivery, and even damage the electronic components orbiting in satellites. During a particularly powerful magnetic storm on the sun in March of 1989, the U.S. Air Force temporarily lost track of more than 2,000 satellites, and powerful currents induced in the ground in Quebec, in their hydroelectric system that is, caused it to collapse for more than 8 hours. The combined cost of the loss of power in the US and Canada alone exceeded $100 million. And before we get to questions, I do just want to go back, let's see. I want to go back just a little bit here. Let's go to, let's see, where am I? Let's go here. So energy is leaving the sun, and we have gravity pulling down. So there's a balance between these forces. So not only is there this gravitational balance between these two forces, but there's also a temperature balance called the solar thermostat. And so basically what this means is the temperature stays about the same through all different layers for a good reason. So for example, if, let's say, the sun were to collapse down a little bit, well, the increased pressure would increase the temperature of the core. And if you increase the temperature of the core, well, we know now that more nuclear reactions are going to start happening. So as a result, more nuclear reactions start happening, and then we start pushing outward even more to balance that bigger pull inward by gravity. And so as we push outward, we cool those layers off, and then things decline. And then if that collapses back down, it heats up, starts new reactions, those reactions push outward, and it's kind of this back and forth. In other words, it's called the solar thermostat. So we have a balance both in temperature and in the basically size and energy output of the sun because of this. And so it's really quite interesting. And so I wanted to throw that in before concluding our lecture, just because I thought it was really useful to discuss. So anyway, if you want to know more about that, just look up the solar thermostat, and you'll have some pretty interesting readings to encounter. Anyway, so let us conclude this lecture with a couple questions. Question number 1. What is the sun's visible surface called? Okay, so whenever we look at pictures of the sun, we're seeing the surface of the sun. And in a picture, another word for picture is photo. The photosphere is what radiates the observable sunlight that produces the bright disk of the sun. The sun's energy is generated in what? So where do we get the energy from? Okay, well, the sun generates its energy in the core, where nuclear reactions are occurring. That energy, if we step back, is then sent outward through the radiative zone. It then cools down and becomes a convective zone. It then reaches the surface, or the photosphere of the sun, and then passes through the chromosphere and corona of the sun to escape. Question 3. What are sunspots? Okay, well, in this case, a simple definition of them is a solar storm. Sunspots are storms governed by the sun's magnetic fields. And last but not least, what are the huge cloud-like structures jutting out from the sun? What are they termed? All right, so in this case, they are known as prominences. And these prominences can lead to things like solar flares and coronal mass ejections. All right, so with this, we'll conclude our lecture. Depending on how much time we have, I might step into 2 more lectures if you're in my course. That would be on light and then stars. But depending on time, we might not get there. So this might be, if you're in my class, the last lecture we get through. But you're still welcome to go to my YouTube channel and watch the remaining very interesting lectures in the course. So, as always, thanks for watching and have a great day.